Electrochemical cells that convert chemical energy into electrical energy through spontaneous redox reactions. From the simple Daniell cell powering telegraph networks in the 19th century to modern lithium-ion batteries, galvanic cells are the foundation of portable electricity. In this presentation, we will explore the fundamental principles of galvanic cells, their components, the thermodynamics that drive them, the Nernst equation that predicts their voltage under any conditions, and their real-world applications. We will work through interactive quizzes and detailed problem solutions covering cell potential calculations, Gibbs free energy, concentration effects, and battery design. By the end, you will understand how a simple strip of zinc and copper can produce an electric current. A galvanic cell, also called a voltaic cell, is an electrochemical device that generates electrical energy from a spontaneous redox reaction. The chemical energy stored in the reactants is converted directly into electrical energy. No combustion or thermal cycle is needed. The key insight is that oxidation and reduction half reactions occur in separate compartments connected by an external circuit, forcing electrons to flow through the external wire rather than transferring directly between reactants. This electron flow is what we harness as electricity. The first true galvanic cell was invented by Alessandro Volta in 1800, consisting of alternating zinc and silver discs separated by brine-soaked cardboard. Today, billions of galvanic cells power everything from pacemakers to electric vehicles. Key points: converts chemical energy to electrical energy spontaneously. Oxidation and reduction occur in separate half cells. Electrons flow through an external circuit, named after Luigi Galvani and Alessandro Volta. Every galvanic cell consists of two half cells connected by a salt bridge. Each half cell contains an electrode immersed in an electrolyte solution containing the corresponding ions. The anode is the electrode where oxidation occurs. It loses electrons and is the negative electrode. The cathode is where reduction occurs. It gains electrons and is the positive electrode. The salt bridge completes the internal circuit by allowing ions to flow between the half cells, maintaining electrical neutrality. Without the salt bridge, charge buildup would quickly stop the reaction. The salt bridge typically contains an inert electrolyte, such as potassium nitrate or potassium chloride in a gel matrix. Electrons flow from anode to cathode through the external wire, while anions flow through the salt bridge toward the anode and cations toward the cathode. Key points: anode is where oxidation occurs, negative electrode. Cathode is where reduction occurs, positive electrode. Salt bridge completes circuit. Electrolyte is the ionic solution. The Daniell cell is the classic example of a galvanic cell. One half cell consists of a zinc electrode in zinc sulfate solution, acting as the anode, and the other half cell consists of a copper electrode in copper sulfate solution, acting as the cathode. At the anode, zinc metal oxidizes. Zn solid becomes Zn2 plus 2 electrons. At the cathode, copper ions reduce. Cu2 plus 2 electrons becomes Cu solid. The overall cell reaction is Zn solid plus Cu2 plus aqueous becomes Zn2 plus aqueous plus Cu solid. The standard cell potential is calculated as E cathode minus E anode equals 0.34 volts minus 0.76 volts equals 1.10 volts. This is the voltage you would measure with a voltmeter connected between the two electrodes under standard conditions. The cell continues operating until the zinc electrode dissolves or the Cu2 plus ions are depleted. Galvanic cells are described using a standardized shorthand notation. The cell diagram shows the anode on the left and cathode on the right, separated by a double vertical line representing the salt bridge. Single vertical lines denote phase boundaries. For the Daniell cell, Zn solid, Zn2 plus aqueous 1 molar, double bar, Cu2 plus aqueous 1 molar, Cu solid. Standard reduction potentials are measured relative to the standard hydrogen electrode, defined as 0 volts. The half-cell reaction is 2H plus 2 electrons becomes H2 gas. A more positive reduction potential means the species is more easily reduced, making it a stronger oxidizing agent. Zinc has E equals minus 0.76 volts. Copper has E equals plus 0.34 volts. Zinc is more easily oxidized, so it serves as the anode. The cell potential is always positive for a spontaneous reaction. E cell equals E cathode minus E anode. The cell potential is directly related to the thermodynamic spontaneity of the reaction through Gibbs free energy. Delta G equals minus NFE. Here, N is the number of moles of electrons transferred. F is Faraday's constant, 96,485 coulombs per mole, and E is the cell potential. A positive cell potential gives negative delta G, confirming a spontaneous reaction. Under standard conditions, delta G naught equals minus NFE naught. The equilibrium constant is related through delta G naught equals minus RT ln K. Combining these gives the Nernst equation for non-standard conditions. Large positive E naught means a strongly spontaneous reaction with a large equilibrium constant. For the Daniell cell, delta G naught equals minus 2 times 96,485 times 1.10 equals minus 212 kilojoules per mole, confirming the reaction is highly spontaneous. The maximum electrical work a cell can perform is Wmax equals minus NFE. The Nernst equation predicts cell potential under non-standard conditions. It accounts for the effect of ion concentrations and partial pressures on the driving force of the redox reaction. The equation is E equals E naught minus RT over NF times the natural log of Q, where Q is the reaction quotient. At 25 degrees Celsius, this simplifies to E equals E naught minus 0.0592 over N times log base 10 of Q. As reactants are consumed and products accumulate, Q increases, the natural log of Q becomes more positive, and E decreases from E naught towards 0. When Q equals K, the equilibrium constant, E equals 0, and the cell is dead, no more useful work can be extracted. The Nernst equation also explains how pH affects cell potential when H+ ions participate in the redox reaction. Concentration cells exploit the Nernst equation to generate voltage purely from a concentration difference of the same ion. Galvanic cells are the foundation of all batteries. Primary cells, which are non-rechargeable, include the Leclanche dry cell, ZnMnO2, 1.5 volts, and alkaline batteries. Secondary cells, which are rechargeable, include lead-acid batteries, PbPbO2, 2.0 volts per cell used in vehicles, nickel-cadmium, nickel metal hydride, and lithium-ion batteries, LiCoO2, 3.6 to 3.7 volts per cell. Fuel cells are galvanic cells where reactants are continuously supplied. Hydrogen fuel cells produce electricity with water as the only byproduct. Beyond batteries, galvanic cells are used in corrosion protection. Sacrificial anodes protect steel ships and pipelines, electroplating, and biological systems. The electron transport chain in mitochondria is essentially a series of biological galvanic cells. Understanding galvanic cells helps us design better energy storage and combat unwanted corrosion. This annotated diagram shows the complete Daniell cell in operation. Zinc atoms at the anode surface lose 2 electrons each and dissolve into solution as Zn2+ ions. The released electrons travel through the external wire toward the copper cathode. At the cathode, Cu2+ ions from solution accept these electrons and plate out as solid copper metal. The salt bridge containing potassium nitrate maintains charge neutrality. K+ ions migrate toward the cathode compartment to balance the loss of Cu2+, while no 3- ions migrate toward the anode compartment to balance the excess Zn2+. The voltmeter reads 1.10 volts under standard conditions. This simple but elegant system demonstrates how chemical energy is transformed into a flow of electrons that can power an external device. Quiz question 1. In a galvanic cell, oxidation occurs at which electrode? Option A, cathode, where electrons are gained. Option B, anode, where electrons are lost. Option C, salt bridge, where ions flow. Option D, voltmeter, where potential is measured. Take a moment to think about your answer. The correct answer is B, anode. Oxidation always occurs at the anode, which is defined as the electrode where electrons are lost. The anode is the negative electrode in a galvanic cell. Reduction occurs at the cathode, which is the positive electrode. A useful mnemonic is an ox, anode equals oxidation, and red cat, reduction equals cathode. Quiz question 2. What is the standard cell potential of a Daniell cell? Option A, 0.34 volts. Option B, minus 0.76 volts. Option C, 1.10 volts. Option D, 0.00 volts. Take a moment to think about your answer. The correct answer is C, 1.10 volts. The standard cell potential of the Daniell cell, the ZNCU system, is 1.10 volts. This is calculated as E cathode minus E anode equals 0.34 volts minus 0.76 volts equals 1.10 volts. The positive value confirms the reaction is spontaneous under standard conditions. Quiz question 3. What is the function of the salt bridge in a galvanic cell? Option A, to provide electrons to the external circuit. Option B, to prevent the solutions from mixing while allowing ion flow. Option C, to increase the voltage of the cell. Option D, to convert electrical energy into chemical energy. Take a moment to think about your answer. The correct answer is B. The salt bridge serves two critical functions. First, it physically separates the two half-cell solutions to prevent direct mixing, and second, it provides a pathway for ion migration to maintain electrical neutrality. Without it, charge buildup would stop the electron flow within seconds. Quiz question 4. According to the Nernst equation, when Q equals K in a galvanic cell, option A, E equals E naught. Option B, E equals 0 and the battery is dead. Option C, the cell voltage doubles. Option D, the reaction reverses spontaneously. Take a moment to think about your answer. The correct answer is B. When Q equals K, the reaction quotient equals the equilibrium constant, meaning the system is at equilibrium. At equilibrium, E equals 0, because there is no net driving force for the redox reaction, the battery is fully discharged. The Nernst equation gives E equals E naught minus RT over NF times ln K equals 0, because E naught equals RT over NF times ln K equals 0, because E naught equals RT over NF times ln K. Quiz question 5. Which statement about the Gibbs free energy cell relationship is correct? Option A, delta G equals plus NFE. Positive E gives positive delta G. Option B, delta G equals minus NFE. Positive E gives negative delta G. Option C, delta G equals minus NF over E, inverse relationship. Option D, delta G is independent of cell potential. Take a moment to think about your answer. The correct answer is B. The correct relationship is delta G equals minus NFE. Since the cell potential E is positive for a spontaneous reaction, delta G is negative, confirming spontaneity. The negative sign is crucial. The more positive the cell potential, the more negative, and thus more spontaneous, the Gibbs free energy change. Problem 1. Cell potential. Calculate the standard cell potential for a galvanic cell consisting of an Al electrode in Al3+ and an Ag electrode in Ag+. E naught for Al3+/Al equals minus 1.66 volts. E naught for Ag+/Ag equals plus 0.80 volts. Step 1. Identify the anode and cathode. Ag+/Ag has E naught equals plus 0.80 volts, more positive, so it is the cathode where reduction occurs. Al3+/Al has E naught equals minus 1.66 volts, more negative, so it is the anode where oxidation occurs. Step 2. Write the half reactions. Anode oxidation. Al solid becomes Al3 plus aqueous plus 3 electrons. Cathode reduction. Ag plus aqueous plus electron becomes Ag solid. Step 3. Balance electrons. The LCM of 1 and 3 is 3. Cathode times 3, 3 Ag plus aqueous plus 3 electrons becomes 3 Ag solid. Step 4. Calculate E naught cell. E naught cell equals E naught cathode minus E naught anode equals 0.80 minus 1.66 equals 0.80 plus 1.66 equals plus 2.46 volts. The final answer. E naught cell equals plus 2.46 volts. The positive value confirms a spontaneous cell. Problem 2. Gibbs free energy. Calculate delta G naught for the Daniell cell at 298 Kelvin. Cell reaction. Zn solid plus Cu2 plus aqueous becomes Zn2 plus aqueous plus Cu solid. E naught equals 1.10 volts. F equals 96,485 coulombs per mole. 1 joule equals 1 volt coulomb. Step 1. Determine N, the number of electrons transferred. Zn solid becomes Zn2 plus 2 electrons, and Cu2 plus 2 electrons becomes Cu solid. So N equals 2 electrons. Step 2. Apply delta G naught equals minus NFE naught. Delta G naught equals minus 2 times 96,485 coulombs per mole times 1.10 volts. Step 3. Multiply. Delta G naught equals minus 1,29 set 0 times Gene del Deu equals minus 212,267 joules per mole. Step 4. Convert to kilojoules per mole. Delta G naught equals minus 212,267 divided by 1,000 equals minus 212.3 kilojoules per mole. The final answer. Delta G naught equals minus 212 kilojoules per mole. The negative delta G naught confirms spontaneity. Problem 3. Nernst equation. Calculate the cell potential at 25 degrees Celsius for the Daniell cell when the concentration of Cu2+ equals 0.010 molar and the concentration of Zn2+ equals 2.00 molar. E naught equals 1.10 volts. N equals 2. Step 1. Write the Nernst equation at 25 degrees Celsius. E equals E naught minus 0.0592 over N times log base 10 of Q. Step 2. Determine the reaction quotient Q. The cell reaction is Zn solid plus Cu2 plus aqueous becomes Zn2 plus aqueous plus Cu solid. Q equals the concentration of Zn2 plus divided by the concentration of Cu2 plus equals 2.00 divided by 0.010 equals 200. Step 3. Substitute into the Nernst equation. E equals 1.10 minus 0.0592 divided by 2 times log base 10 of 200. Step 4. Calculate log base 10 of 200. Log base 10 of 200 equals log base 10 of 2 times 10 to the 2 equals 0.301 plus 2 equals 2.301. Step 5. Complete the calculation. E equals gener del 10 minus 00. 2 9 6 times 2.301 equals gener del 10 minus 00 6 8 1 equals 1032 volts. The final answer? E equals 1.03 volts. The cell voltage drops as products accumulate. Problem 4. Equilibrium from E naught. Calculate the equilibrium constant K at 298 Kelvin for the Daniell cell reaction. E naught equals 1.10 volts. N equals 2. R equals 8.314 joules per mole Kelvin. F equals 96,485 coulombs per mole. Step 1. Use the relationship between E naught and K. E naught equals RT over NF times the natural log of K. Step 2. Rearrange to solve for ln K. ln K equals NF E naught over RT. Step 3. Substitute values. ln K equals 2 times 96,485 times 1.10 over 8.314 times 298. Step 4. Calculate the numerator. NFE naught equals 2 times 96,485 times 1.10 equals 212,267 joules per mole. Step 5. Calculate the denominator. RT equals 8. 3, 1, 4 times 298 equals 2.478 joules per mole. Step 6. Complete the calculation. ln K equals 212,267 over 2,478 equals 85.66. K equals e to the 85.66 equals 1.5 times 10 to the 37. The final answer? K equals 1.5 times 10 to the 37. The very large K shows the reaction is essentially complete. Problem 5. Concentration cell. A concentration cell consists of 2 hydrogen electrodes. One half cell has the concentration of H plus equals 1.0 molar. The other has the concentration of H plus equals 0.0010 molar. Calculate the cell potential at 25 degrees Celsius. The cell is PT, H2 gas at 1 atm, H plus aqueous, double bar, H plus aqueous, H2 gas at 1 atm, Pete. Step 1. Understand the concentration cell principle. Both electrodes are PTH2, E naught equals 0 for both half cells. The dilute side at 0.0010 molar acts as the anode, oxidation. The concentrated side at 1.0 molar acts as the cathode, reduction. Step 2. Write the Nernst equation for the cell. E equals minus 0.0592 over N times log base 10 of the concentration of H plus at the anode divided by the concentration of H plus at the cathode. Step 3. Substitute values. N equals 1 for H plus for H2. E equals minus 0.0592 divided by 1 times log base 10 of 0.0010 divided by 1.0. Step 4. Calculate the log term. Log base 10 of 0.0010 over 1.0 equals log base 10 of 0.00